We'll wait for a few minutes for others to join.
Okay, sir. Okay.
All right, let us start. So, welcome to week 11 tutorial for the course IC Engine and Gas Turbine. So, in the previous tutorial, we started with the compressor section towards the end, where we discuss about the reciprocating compressor, where we calculated the work input with and without clearance volume in two cases. And towards the last, we have seen the efficiency, volumetric efficiency of a reciprocating compressor. So I hope everyone is regular to the lecture videos as well as tutorial videos on by the professor on the NPTEL portal. And as well as those who are unable to watch my videos directly, you might have got the mail from the NPTEL team with the Google Sheet where you have links of all the videos as well as the PDF notes Google Drive link. And if you are new, you can watch my videos on my YouTube channel NPTEL with Varnit. And in the playlist section, you can see for the corresponding course all the week-wise videos, tutorial videos. And in each video description, you can see the Google Drive link for the PDF notes as well. All right, let us start. Let me share my screen. Can you please confirm is my screen is visible or not? Santosh, can you confirm? I hope so. My screen is visible right now. All right. And my audio is also there. Clear? All right. Okay. So let us start with the multi-stage compression. Multi-stage compression So instead of increasing the pressure from the compressor in a single stage using a single compressor, we can use more than one compressor. And with the increase in value of the pressure in a single stage compressor, the volumetric efficiency decreases. So beyond a particular value of a pressure ratio, multi-staging is necessary. Otherwise, the temperature will reach very high with a single stage, and it can lead to metallurgical very high temperature than the metallurgical conditions of the material used in the compressors. Okay, so there are in single stage compressor you can use increase the pressure up to 5.6 bar suppose, and in dual stage you can increase from 5.6 to 335, and in triple stage and higher 35 to 180 bars as well. Okay, so let me just write these point. With increase in value of pressure, I hope I'm clearly audible. Hello? Am I clearly audible?
Yeah, sir, you are clearly audible. Audible.
Okay. Okay. With the increase in value of pressure in a single stage compressor, the volumetric efficiency decreases beyond a particular value of pressure ratio. So multi-stages. So multi-staging is necessary. Okay. As it helps in reducing the construction cost. The construction cost of the material. At any point of time, if my voice goes, please let me know. And leakage across the piston. Leakage across the piston. Okay. So for a single stage compressor, SS, the pressure can be 5.6 bar. For a dual stage, it can be from 5.6 to 35 bars. And for higher tertiary state, it can be 35 to 180 bars. All right. So let me show a diagram. It will be similar as that of the intercooling in the turbine we used to do. Okay. So again, first what we have a compressor one, suppose compressor one. Then outlet of this compressor is connected to a intercooler. Outlet is connected to intercooler where the temperature is decreased. Intercooler where the temperature is decreased at a constant pressure. Okay, so let us say this is 1, the outlet is 2. Then when we pass through an intercooler, then we again pass it through another compressor number 2. Compressor number 2. Inlet of it, this is 3. Then the exit from this is 4. So you can do multiple intercoolings as well as connect through a multiple number of compressors as well. Okay. So how will the graph look like? We have already seen in the turbines case. How will it look like? Suppose if I want to plot, sorry, so pressure versus volume, or sorry, temperature versus entropy, we have seen how does it look like. So first, from 1 to 2, the pressure increased. It will be the same as that of the intercooling in the turbine. So 1 to 2, pressure increased as well as temperature rise. Then it passed through a intercooler. At same pressure, the temperature is decreased to 3. And then again pressure is increased as well as temperature increased when it passed through a second compressor. Okay. All right. And similarly, the further the graph will look like. Okay. All right. So we will make few assumptions here when we are dealing with a compressor. Let me write assumptions. So first is ideal gas law can be applied. That is P1 V1 is equal to MRT1. Okay. And P3 V3 is equal to MRT3. P3 V3 is equal to MRT3. Okay. At inlet. Then perfect intercooling. That means your temperature at 1 and 3 are equal. So T1 is equal to T3. That is perfect intercooling. We have derived these conditions, if you remember, in previous tutorial, how the perfect intercooling is achieved. Then we say that pressure. Uh, so these are the assumptions which we are taking. We can also now say that P1 and P1 is the lowest pressure. P2 and P3 are the intermediate pressures. P2 is equal to P3 is equal to P intermediate, and P4 is again highest pressure. That is P high. Okay. Also, we can say our index. Let us take n minus 1 by n. That is your polytropic index to be x. Instead of writing again and again n minus 1 by n, let us say it is a x. Okay. Now, as we have seen that with the help of intercooling, the work reduces. We have seen this in turbine. Same thing happens here. Okay. Turbine phase. Why? Let me recall that by making a graph again of pressure versus volume. So first we increase the pressure from 1 to 2, volume decreased 1 to 2. Then at constant pressure, the temperature was decreased at an intercooler. Then finally, pressure was increased from 3 to 4. Okay. And when you draw for the open system device, that is your compressor, it is over the VDP, change in the pressure. Okay. If you would have gone directly instead of 1 to 2 dash and increased till that temperature. So this was a reduction in the work. Okay. Reduction in the work. So this is your P1 is equal to P lower, and this is P4 is equal to P higher. Same terminology as that in the above graph I'm taking. Okay. So there are two compressors right now, the compressor 1 and compressor 2. So net work input will be work done by compressor 1 plus work done by compressor 2. And we have seen that what is the work done by a compressor. Okay. With a clearance volume or without a clearance volume. We have derived in the previous tutorial. So it is n by n minus 1, or we can say n times the work of close. Okay. That is n by n minus 1 times P1 V1 into pressure ratio P2 by P1 power x minus 1. Okay. This is work done by compressor 1, and work done by compressor 2 will be n minus 1 P3 V3 into P4 by P3 power x minus 1. This is your net work input to the compressor. Okay. And we are saying that P1 V1 can be written as using an ideal gas law MRT1. Let us write like this. So work input will be n by n minus 1 times mRT1 P2 by P1 power x minus 1 plus n by n minus 1 into mRT2 into P3 by P4 by P3 P4 by P3 power x minus 1. Okay. Now let us take n by n minus 1 common. Okay. So this can be written as 1 by x because n minus 1 by n is taken as x. And we have taken, okay, so one mistake I have done, probably just wait a second. We have taken n minus 1 by n is x. Okay. And we are saying that it is perfect intercooling. So T1 is equal to T3. This was T3. So this and this is equal in our assumption for perfect intercooling. Okay. So let us write this as 1 by x. So this can be written as mRT1 can be taken common by x times P2 is your P intermediate, P1 is your P lower, power x minus 1. Okay. Plus P4 is your P higher, P3 is your P intermediate, power x minus 1. All right. So this minus 1 can be written as minus 2 altogether. mRT1 by x, Pi by P lower, power x plus P higher by P lower, or Pi power x minus 2. Okay. Now you want to get the minimum work input. Okay, suppose. So what will be the condition for a minimum work input? What is the only variable in this complete equation? This is known, this lower is known, this higher is known, this is a constant, x is also known for a particular polytopic. So only variable here is your Pi. So you can differentiate for a minima this work input with respect to Pi. Okay. So let me, for minimum work, let me write for minimum work input T of dWIP by Pi is nothing but, if you differentiate it, you will get your expression as to be 0. Therefore, 1 by P lower power x into x times Pi power x minus 1 plus P higher power x minus x Pi power minus x minus 1 equal to 0. Okay. And if you simplify it, your final intermediate pressure will be P higher into P lower. Okay. So this is your intermediate pressure. Okay. So this is the same condition we got with the intercooling also when we did it with the turbines. Okay. Right. So intermediate pressure is under root product of under root of lower and higher temperature. Same condition again. Okay. All right. I hope this is clear. Now let us write one point as note. Okay. So when I am doing multi-staging, instead of 2 compressor, I can have more than 2 compressor, 3 compressor, 4 compressor. All right. So let us say multiple compressor are there, then what will be your overall pressure ratio in that scenario? So let me draw a diagram. Pressure versus volume. Let us say once I increase the pressure, then intercooling, pressure, intercooling, pressure. Okay. फिर उसके बाद then 1, 2, 3, 4, 5, 6, let us say. Okay. And And let us say these are your limits. Okay, P1, P2, P3, P4, P5, P6. So overall pressure ratio, that is, sorry, overall pressure ratio will be from P6 to P1 can be written as product of each stage pressure ratio. Okay, pressure ratio in the each stage. So that is P2 by P1 into P4 by P3 P2 by P1, P4 by P3, and P6 by P5. Okay, P6 by P5. Okay, and we know that P1, P2, and P3 are same. P4 and P5 are same. So P2, P3 same, P4, P5 same. So it is again P6 by P1 only. Okay, mathematical also if you see. Okay. So we get our final pressure ratio P6 by P1 in the terms of pressure ratio in each stage. Why it is not working? Let me see. Oops. Oh, I think everything. Okay, I'll write once again. So it is P2 by P1, P4 by P3, and P6 by P5. So we can write the overall pressure ratio is nothing but product of pressure ratio in each stage, pressure ratio in each stage power the number of stages. Okay, power n. Okay, n is the number of stages. So it can also be written as P6 by P1 is nothing but P2 by P1 power 3. Okay, so this n is nothing but your number of stages. Okay, this n is nothing but your number of stages. Since P2 by P1 is equal to P4 by P3 is equal to P6 by P5. Since P2 by P1 is equal to P4 by P3 is equal to P6 by P5. And this is only when we are assuming that perfect intercooling is there. Now, why this is equal? Because 2 and 3 are intermediate pressures. Can I write P2 and P1 as P intermediate by P lower, this term, which will be nothing but P higher, P lower by P lower. That is nothing but P higher by P lower in the ratio. Similarly, if you go for this can also be written as from 3 to 4, P higher by P intermediate. Again, P higher by under root of P higher, P lower. Okay, so this will be under root of P higher by P lower. So this and this again is coming out to be same. So just to prove, okay, just remove this and write up in the form of point. Okay. So let me write the first point of the note, that is for minimum work input, minimum work input with perfect intercooling. The pressure ratio in each stage is same. Okay, is same. Next point is that this is the pressure ratio. What about the work? So next point of the note is if I want to see for the work from 1 to 2, suppose is nothing but n by n minus 1 into P1 V1, P2 by P1 power n minus 1 by n minus 1. Similarly, P1 V1 can be written as MRT1. Okay. So but for and similarly here for work 3 to 4 is nothing but n by n minus 1 P3 V3 P4 by P3 power n minus 1 by n minus 1, and P3 V3 can be written as MRT3. For perfect intercooling, T1 is equal to T3, and also pressure ratios are also same as we have just derived above. So that means work of 1 2 is equal to work of 3 4, because this is same in terms of MRT, this is also same, so whole work input is same. Okay, you can directly write total work input will be, can be written as n into work input in each stage. Okay. Each, but mind my words that I am talking about when there is perfect intercooling. Okay, so total work input will be n times work input in each stage. So for perfect minimum, for minimum work output with perfect intercooling, work done in each stage is same. Let me write this point also. For minimum work input, for minimum work input with perfect intercooling, work done in each stage is same. And the best case scenario will be if the condition is isothermal. Why? So again, from a thermodynamic point of view, in my lectures I have explained that the isothermal work done is lesser. If you plot on PV, okay, so work for a compression, this is PV raised to power n is equal to constant, a polytropic process, and this is PV is equal to constant when n is 1 for isothermal case. So this is a reduction in the work input. Okay, so if you see, area for PV is equal to constant is less compared to PV raised by n is equal to constant. All right. So isothermal compression is best whenever you are dealing with the compression state. So isothermal compression. So you can get how your slopes and everything. You just differentiate it on left and right hand side with respect to P and V both, because both are variable, and you will get the slope. The slope of a isothermal is lesser compared to slope of your slope of this curve is lesser compared to that of your polytropic. That's why the area will be also coming out to be less. Therefore, best isothermal compression is best for work input. Okay. Next point, third point of the note. With the use of multi-staging, we can reduce the leakage across the piston, and it also helps in saving the construction cost of the material. I've written this point already, and we have seen the volumetric efficiency is 0. So when will be the volumetric efficiency will be 0? So we had a expression for a volumetric efficiency which we derived in the last tutorial. 1 plus C minus C times P2 by P1 power 1 by N. For volumetric efficiency to be 0, put this expression to be 0. P2 by P1 power 1 by N equal to 0. So take out C common, 1 minus P2 by P1. Sorry. take this term on the right hand side or vice versa. So this will be C times P2 by P1 power 1 by n minus 1 is equal to 1. From here, your pressure ratio will come out to be 1 plus 1 by C power. This is your condition for zero volumetric efficiency if it is asked. Any doubts still here for the multi-stage compression? If you have any doubts, please ask. Santosh, any doubts? Am I audible? Hello? Okay. Now let's come to the concept of free air delivery. Free air delivery. What do we mean by free air delivery? So it is a standard practice when we are getting the delivery volume reduced to 1 bar pressure and 15 degrees Celsius temperature. That corresponding volume is known as free air delivery. Okay. So why it is this concept has been incorporated so as to measure the so as to compare the handling capacity of different compressors. Okay. So let us say we have two vehicles. Okay, two-wheelers are there. Let us suppose we have two bikes. Okay, one bike is at the flat region and one bike is at a uh, mountainous region. Okay, same bike at two different locations will have different output because of the different climatic conditions. And what do I mean by the output? That is your average or mileage. Because ambient conditions may be a higher side on the higher side for the flatter region and on the lower side for on the mountainous region. So that is why you can have a different outputs in the form of mileage for the same vehicle. So that is why we need to have some standard to compare. So let me write. It is the delivery volume reduced to 1 bar pressure and 15 degrees Celsius temperature, and the corresponding volume is known as free air delivery. FA, let me write in a short form, is known as FAD. It is measured to compare the volumetric handling capacity of different compressors working under different conditions. Okay, working under different conditions. So let us make a pressure volume plot for the reciprocating compressor with the clearance volume. This is PV, 1 to 2 compression, 2 to 3 exhaust, 3 to 1 expansion, and 4 to 1 section. 1, 2, 3, 4. Okay, and let us say the conditions are 1 bar, 15 degrees Celsius. Okay, let's on using the ideal gas law, that is PV is equal to mRT. Mass will be PV by RT. Okay. So let us say P final, V final to that of RT final. These are your conditions in the final. Can be written in terms of P2 V2 minus V3 that of RT2 RT2. So R and R can get cancelled out, and P final V final by T final can be written as P2 V2 minus V3 by T2. Okay. Similarly for V1 V4 also you can write. So it can be written in the form P1 V1 minus V4 by T1 is equal to P2 V2 minus V3 by T2, and this can be equal to PF by TF. And these are your standard conditions. That is when you are comparing with the free air delivery. Okay, A, T conditions. Now the point may rise that why I am not writing P1 V1 by T1. Why I am writing P1 V1 minus V4? Because this is a, when I'm saying V1 minus V4, so this is a process from 4 to 1. That is a section process. Okay. So in a cycle, we have a one process, and we say these 1 and 4 are the point functions. So the net difference will give you the net suction volume that has been actual suction or actual swept volume from the compressor. Similarly, V2 minus V3 is also the same scenario. That is, it is a part of a one process of that cycle. Okay. And these are nothing but your point functions. Okay. So mass flow rate at entry of compressor and its exit are equal and are also equated and compared with that of free air delivery conditions. So this implies I'm just comparing the mass at entry and exit. So therefore mass flow rate at entry of compressor and its exit are equal, and are also equated and compared with free air delivery condition. Okay. Now, how do we get the cylinder dimensions for the multi-stage compressor? Right? What should be the dimension of that cylinder of that compressor? Let us see. Cylinder dimensions for multi-stage compressor. So again, I'm saying that mass flow rate will be same across all the cylinders. Okay, whatever the mass has been passed through the first cylinder, it will be equal from the second as well as third and so on, depending on number of the multi-staging you are doing. So mass flow rate from all compressor will be equal in multi-stage compression cycle. Okay, that is mass flow rate MA1 dot is equal to MA2 dot is equal to MA3 dot, let us say. Okay, and since we know that density is nothing but mass upon volume, so mass can be written in terms of density and volume. Therefore, we can say mass flow rate is of the first one is rho 1 VA1 is equal to rho 2 VA2 is equal to rho 3 VA. Okay. And how you will get your rho? So again, since we know that PV is equal to MRT, so pressure can be written as M by volume RT, and mass by volume is nothing but your density. So this you can say that pressure is rho RT. So finally we can say that density is nothing but P by RT. Okay. So put this densities. So it can be P1 by written as P1 by RT1 PA1 is equal to P2 by RT2 PA2 is equal to P3 by RT3 VA3. R cancels out. So we are left with P1 VA1 by T1 is equal to P2 VA2 by T2 is equal to P3 VA3 by P3. And if I say I have a scenario of a perfect intercooling, for perfect intercooling, I know that T1 is equal to T2 is equal to T3 in all the compressors. Okay. It will be equal. Okay. So how it will be shown? So this is my first stage compression, then second stage compression, then third stage compression. Let us say it is from 1 to 1 dash, from 2 to 2 dash, from 3 to 3 dash. All these are equal T1, T2, and T3 over a temperature entropy plot. Okay. T1, T2, T3 all are equal. So we can say that these denominators will cancel out for that. Therefore, we are just left with P1 VA1 is equal to P2 VA2 is equal to P3 VA3. Okay. Now we know that what is a volumetric efficiency? Volumetric efficiency is nothing but V actual with to that of V swept. Okay. VA1, VA2, VA3 are your actual volumes, and Vs is your swept volume for each cylinder. So what will be your actual volume in terms of volumetric efficiency? And put this back again. So you will get E1 volumetric efficiency of the first compressor times swept volume of the first compressor cylinder, P2 efficiency 2 Vs2, P3 efficiency 3 V3. Okay. Now what is our swept volume for a cylinder? We have seen in the IC engine as well. That is your pi by 4 d square L. Okay. So it will be P1 volumetric efficiency 1 pi by 4 d1 square L1 is equal to P2 volumetric efficiency 2 pi by 4 d square L2 is equal to so on. Okay. Now your pi by 4 can get cancelled out, and we can write in terms of, if let us say the length of each cylinder is same, then what will be your diameters? If we say in that set, what do I mean by that? The volumetric efficiency for all the compressors is same as well. So let us assume if C and N are same, C and L are same for all compressors. C and L are same for all compressor. That is, what is your volumetric efficiency? 1 plus C minus C minus P2 by P1 power, or P higher by P lower power 1 by N. So volumetric efficiency will be same in all the scenarios as well as your length. So therefore, you can say that P1 time D1 square is equal to P2 time D2 square is equal to P3 time D3 square. So this is your condition that says that you don't have to learn this condition. Always remember that mass flow rate will be equal. Always derive from this. But this is the scenario where you can say cylinder dimensions for multi-stage compression can be achieved. That is P into D square is equal to constant. Any doubts still here? Santosh, can you unmute yourself? Am I audible? Okay. All right. I hope this is pretty much clear. Now we are done with the multi-staging and the free air delivery concept in it. Now let's proceed to some numericals, good numericals. I'll give you a few questions and then we will proceed to rotary compressors. We will finish up with the reciprocating part. Determine a question. Determine minimum number of stages required in an air compressor in which air enters at a pressure of 1 bar and a temperature of 27 degrees Celsius and delivers at 180 bar. Maximum discharge temperature is limited to 150 degrees Celsius and consider the index of polytropic expression as n is equal to 1.25. You can assume perfect, or let me write consider index of polytropic compression (1.25) and assume perfect and optimum intercooling between stages. Okay, try this question. I'll give you a few minutes to do. Meanwhile, I'll be back. Just hold on. Okay, have you done? Have you solved what will be the minimum number of stages? Santosh, Priya, what will be the answer? Okay, let us solve. It is said that you need to find the number of stages required in this compressor, which is a multi-stage compression happening. What will be the number of stages required? And air enters at T1 27 degrees Celsius and P1 1 bar, delivers at 180 bar. So your final pressure is 180. Maximum discharge temperature is given 150 for each stage, and gamma is 1.25. Assume perfect intercooling. All right. So it's a very pretty simple question. You are given that P1 is 1 bar, T1 is 27 degrees Celsius, Pn that you don't know how many stages are there, but your final pressure is 180 bars. Okay. You know that Pn by P1 is 180 by 1, that is 180 itself. Okay. For perfect and optimum intercooling scenarios. And you know that T2 by P1 can be written as T2 by T1 power n by n minus 1. Right? So here you know that 423, 180 plus 273, sorry, 227 degrees Celsius and 27 degrees Celsius, and maximum temperature is 150. Yeah, 150 plus 273 by temperature, initial temperature is 27 plus 273 power 1.25 by 1.25 minus 1. So from here, you know your P1, so P2 will come out to be 5.57. P2 will come out to be 5.57. Okay. All right. So we know that the pressure ratio, the overall pressure ratio in multi-staging is pressure ratio in each stage to the power of n, number of stages required. So Pn by P1 can be written as P2 by P1 power n. So you know that Pn by P1 is 180 by 1, and P2 by P1 is nothing but 5.57 by 1 power n. Solve this, take the log, and you will get n as 3.02. But if it's greater than 3, then you have to give your final answer as 4, because there is nothing like 3.02 compressor. If it's more than 3, that means you have to use 4 compressors. 4 times multi-staging you are required to do. Okay. I hope there is no doubt. Pretty much easy. This will be your answer. All right, next question. A single stage reciprocating compressor having bore of 200 mm, and stroke of 300 mm. It runs at a speed of 500 rpm. Clearance volume is 5% of swept volume. And value of index is 1.3. Intake pressure and temperature are 97 kilopascal and 20 degrees Celsius. And delivery pressure is 550 kilopascal. If free air delivery conditions are 101.325 kilopascal and 15 degrees Celsius, then find first free air delivery in meter cube per minute, second power required, third volumetric efficiency. Okay, do this question. Simple question. Take your time, do this. It's a simple as well as a good question. Everything is given to you. Done? Any doubts? What is the answer? Okay, let us solve this. So we are given a single stage reciprocating compressor. The bore and the stroke is given, the diameter and the L. RPM is given 500 RPM. Clearance volume is 5% of the swept volume. That is clearance ratio is given to you. Polytropic index 1.3 is given. Intake pressure and temperature are given, P1 and T1. And delivery pressure is given, 550 kilopascal. Free air delivery conditions are given. We need to find what is free air delivery in meter cube per minute, power required, and the volumetric efficiency. Let us solve this. Solution. So let us write what is all given to us. 4 is given 0.2 meter, 200 mm. Length is given 300 mm, so 0.3 meter. Then RPM is given to you, that is 500 RPM. Index is given 1.3. P1 is given 97 kilopascal. T1 is given 293 Kelvin. G2 is given delivery pressure 550 kilopascal. Free air delivery conditions are given and clearance ratio, that is 0.05, that is VC by V swept is given to you. Okay. Now let us solve. So what will be your swept volume? So V swept is nothing but pi by 4 T square L into N by 60. So what is 0.2 square into 0.3 into 500 RPM by 60. Okay. Your final answer will be 4.712 meter cube per second. Oh, in meter cube per minute it has been asked. Let us keep it in meter cube per minute for now. That is your V swept. You know that clearance ratio is 0.05. That is V clearance, that is V3 by swept is V1 minus V4. Okay. Also, let us not write in this term. Let us first find the volumetric efficiency. 1 plus C minus C, P higher by P lower, power 1 by N. So 1 plus 0.05 minus 0.05 times P higher is 550, P lower is 97 kilopascal by 1.3. So from here, your volumetric efficiency will come out to be 86%. That is your answer. Then free air delivery condition has been asked. So we can write P final V final by T final is nothing but P1 V1 by T1. And this is nothing but your actual. Okay. So how you will get your actual, since volumetric efficiency is V actual by V swept. So you can write P1 volumetric efficiency time V swept by T1 P final V final by T final. Okay. From here you will calculate your final VF, that is 101,325 into VF, the free air delivery conditions I am writing, to that of 288 is equal to what is your initial pressure, 97 kilopascal. V actual you have got as volumetric efficiency is 0.86 times V swept you have got as 4.71. Okay, 4.712. So that of what is your initial temperature, 293. On solving, you will get your free air delivery in terms of meter cube per minute, 3.81 cube per. This is your answer. Then it has also been asked the power. So power is nothing but work input per second. Okay. So what is your work? Power is work input by 60, because what is work input? P1 V1, and V1 is nothing but your V actual, and V actual itself has your in terms of meter cube per minute. So you'll write in meter cube per second. So that's why I have divided by 60. And in V calculation, already we have seen the RPM. So we will not write RPM once again. So P1 V actual by into N by N minus 1 times P2 by P1 power N minus 1 by N minus 1. Put all your values. V actual is nothing but, how will you get your V actual? So from here, V actual is 0.86 times 4.712. That was your 4.05 meter cube per minute. So putting all your values, you will get your power required, that is 13.967 kilowatt. That is your, okay. Now in this we have, for a compressor, let us draw an actual indicator diagram also. Okay. As we have seen in the IC engines, we have actual uh, pressure versus volume plot compared to the theoretical one. So similarly, same scenario will be here. Actual indicator diagram. So in actual condition, there will be always be resistance because of the presence of the friction during the suction and the discharge, due to which the actual work of the compressor, work input of the compressor is always going to increase. So in actual, let me show you in the form of a diagram. First of all, pressure versus volume plot. This is the pressure versus volume. So theoretical cycle was looking like this: 1 to 2, 2 to 3, 3 to 4, and 4 to 1. 1, 2, discharge, expansion, and suction. Okay. But in actuality, when you are, the suction process is happening, the pressure inside the cylinder should be lower than that of outside ambient. Okay. So pressure should be lower, as we have seen in the IC mechanism. Then your compression happens. So your pressure of suction should be lesser. This is your change in pressure difference in suction, delta P S. And similarly, when you are delivering out of the compressor, that means your pressure inside cylinder must be higher compared to the ambient. So then because of that pressure difference, you will be able to deliver outside. So this is your pressure in delivery, delta P D. Okay. More pressure required to discharge and lesser pressure required for suction. Okay. So in actual condition, there was some resistance offered by suction and discharge value, due to which actual to compressor work input increases. How you can see again, T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. Okay. So if your temperature increases, pressure increases, P2 increases, and your work input is again in terms of pressure ratio, so that also increases. Okay. One point to note here before starting rotary compressor is that isothermal efficiency. If someone asks what is isothermal efficiency, so isothermal efficiency, isothermal efficiency is defined as the ratio of isothermal work. And now we will start with rotary compressors after this. Ratio of isothermal work, isothermal work, actual work. And generally its value varies from 80 to 85%. Generally, isothermal efficiency varies from 80 to 85%. Okay. All right. So now we are done with the reciprocating compressor, and let us start with the rotary compressors. Rotary compressors. Rotary compressor. The topic is rotary compressor. So when you are dealing with the pump, when you are dealing with the turbines, then your working fluid, that is your air, is your system. And when you are dealing with the pumps or compressor, water or air is your again system. So in turbine, you are getting the work done from the system, but in pump or compressor, you are providing work to the system. Okay. So what is the principle of the rotary compressor, rotary machine? Let us first understand that. What is the principle of a rotary machine? Principle of rotary machine. So let us assume there is a fluid which enters at a section 1. Let me make a rotary machine first of all. Make a rotary machine. Yes. It is rotating at a speed omega. Okay. The rotary machine is rotating at a speed omega. Let us say the fluid enters at a velocity 1, absolute velocity 1, and exit at an absolute velocity 2. Okay. Fluid enters at the section 1 and leaves at section 2. Let us say this was your section 1, and it enters at a velocity, suppose 1, okay, at the section 1, and leaves at section 2. Let us say this is your section 2. Okay. And both the sections have radius r1 and r2 from the center of the rotor. And under the equilibrium condition, it is running at a constant speed omega, angular speed omega. Then your absolute speeds v1 and v2 can be resolved in two ways: the vertical component and the horizontal component. So first is the horizontal component of this and the vertical component of this. Okay. Let us say your horizontal component is called vw1 and vertical component is called vf1. Okay. Similarly here, the exit velocity also have two components, vw2 and vertical components vf2. Okay. Let me write this point first of all. Let us assume fluid enters at section 1 and leaves at section 2 having radius R1 and R2. Under equilibrium condition, it is running at a constant angular velocity of omega, then absolute velocity can be resolved into two components, that is the velocity v, that is either v1 or v2, can be resolved into two components, that is vw and vf, where vw is nothing but your, if I say this is your angle alpha, so v1 will be vw1 cos alpha, sorry, vw1 will be v1 cos alpha. Similarly, vw can be written as v cos alpha and vf can be written as v sin alpha. I'll make the velocity triangle explain, but just I'm trying to give you a basics how the velocity components can be resolved. Okay. So v cos alpha, that is vw, is nothing but your wall velocity or a tangential component. Wall velocity or tangential component of that velocity. And vf is but nothing but your radial or flow velocity. Flow or radial. So radial velocity, whenever a particle is moving in a circular motion, always remember from mechanics that the radial velocity always gives you the change in the direction, and the tangential velocity or the tangential component gives you the change in the magnitude. Okay. So suppose you have a stone tied through a thread, and if you want to rotate that stone, what will happen? That stone has constantly moving in a circular motion will have an absolute velocity, and it has one tangential component and a one radial component towards the center of the thread from where you have picked up and rotating from your axis. The radial component is maintaining that the stone should maintain a circular motion, whereas the tangential component is maintaining that the speed of that circular motion. Okay. And v is nothing but your absolute velocity. Absolute velocity. We have some another terminologies, that is your rotor is also moving with some speed u. Okay. U is your rotor speed. And Vr is nothing but your relative speed. So your rotor is moving at another speed u, whereas your rotor or your blades on that compressor are moving at a speed u in a circular motion. The u is your basically again the tangential component of your rotor. Okay. And there will be a relative velocity between the both of them. Okay. Because working fluid, that is your water or air whatever you are want to compress is moving at a different velocity compared to that of rotor. So how you will get the rotor speed at inlet and outlet? Because at section 1 and section 2, I'm saying that they have different radiuses R1 and R2. So what will be a rotor speed at inlet? Rotor speed at inlet. My whole system is moving at a constant angular velocity omega. No, I'm not talking about the working fluid. I'm talking about the machine. Okay. The rotor speed is moving at velocity, angular velocity that is constant under equilibrium condition at omega. But it will have, because positions of the blades at different section will have different radiuses. So your rotor speed will be u1 will be r1 times omega, and rotor speed at outlet, that is u2, will be r2 times. Okay. Similarly, what will be your angular momentum at the section 1? I'm just giving you a flavor of the basics of mechanics. Okay. Angular momentum at section 1 will be, at section 1 you have two velocities. One is the rotor velocity and the fluid velocity. So there will be a relative motion, and that is nothing but your VR, relative speed, which we have written here. So VR is your relative velocity. So mass flow rate of the fluid which is entering times VR, VW 1 times R1. Why I've written VW1, not V later? Why? Because VW is the component that is responsible for change in the magnitude, okay, not in the direction. So VW is the angular momentum at the section 1 of the fluid. What is the angular momentum at section 1 of the fluid? It is the tangential component into radius into mass flow. And similarly at section 2 it will be mass flow rate will be same, VW2 R2. Okay. And what is torque? Torque can also be written in terms of rate of change of momentum. Torque is nothing but rate of change of angular momentum, not linear, angular momentum. So that is nothing. Mass flow rate times the final is VW2 R2 minus VW1, that is your change, final minus initial. If I want to get the power is nothing but torque into omega, torque into angular velocity. Torque times omega. So put this mass flow rate into VW2 R2 minus VW1 R1 times omega. So if you put this will be mass flow rate into VW2 R2 into omega is nothing but U2. We have just written here. R2 into omega is U2. U2 minus VW1. This is your power. Okay. This is your power. Now you need to have these components, void components and the blade velocities. Okay. So when you are dealing with the compressor, it will be power input, that is change of the VW2 minus U2, VW2 U2 minus VW1 U1, Euler work. And when you are dealing with the turbine, the sign will be changing. Okay. So energy in the compressor at the outlet, the system, your system is your working fluid. That is your water if you are, or gas if you are compressing your gas. So energy of the gas at outlet or the discharge of the compressor or the pump will be higher compared to that of inlet. Whereas in the turbine, energy of the gas or the working fluid that is your system, has a higher energy at the inlet compared to that of a turbine. So there it will be VW1 U1 minus VW2 U2, only a change in the sign. Okay. Now let us make a proper diagram of understanding all these scenarios. That how these will look over the blades. Okay. So let us say make a big diagram here. I need to understand. Okay. Let me make the diagram first. Here I am having the blades. Okay. These are the blades or the vanes on the impeller. Okay. These are the blades or vanes over the impeller. Okay. This is your blade. First, let me. And there is a diffuser which is surrounding it. And diffuser itself has some blades over it. Okay. All right. And then we have a casing like this. So this is nothing but your eye or the rotor. This is your impeller which is moving. These are your blades, impeller blades. This is your diffuser casing and the blades of diffuser. Diffuser blades. This is your diffuser, this whole casing. Diffuser. Okay. And this is your final casing that has a diverging cross section. Okay. So from here to here, the cross section is increasing. Okay. I'll explain the working, don't worry. And this is whole of your casing. Diverging casing. Okay. Diverging casing. All right. So this is the functioning of the compressor. Think it like it is a top view. I'm showing you the top view of this. So this is a top view or front view. But let us assume that it's a top view. So fluid is entering from the bottom of the eye. The impeller is rotating. You are providing electricity. Your pump is working at your home. It is providing electricity. It is absorbing the electricity. The pump runs. How? The impeller starts running. Because of the high speed at the inlet of the impeller, the pressure is reduced. So pressure in the ambient is higher compared to the pressure in the impeller because of vacuum suction. This creates a suction scenario, a vacuum scenario. So water lifts up, it passes through these impeller blades. Those are orange in color. So these impeller plates have two sections, section 1 and section 2. Okay, section 1 and section 2. Let me use some another color. So this has section 1, this is section 2. So if you observe the radius from center of this impeller has R1, suppose this one, this is your R2. So that is why I said two different radiuses are two different sections. So they will have different velocities as well. Okay. R1 and R2 are different. So 1 and section 2. Now the water enters or the air enters through section 1. passes over the blades and exit through a section 2 at a absolute velocity v2. Then it passes through a diffuser. If you see, a diffuser has a diverging section, and diffuser is always fixed. Diffuser doesn't move, only impeller moves. And then that fluid is passed through a diffuser. If it has a diverging section, so to maintain the continuity, that is area into velocity, the same mass flow rate out of it, area has been increased, so velocity has got to eventually decrease. Okay, and because of which the pressure rises. Because of the decrease of velocity, pressure rises, and because now the fluid finally comes out and it again passes through a diverging section, that makes the area more increase, then velocity have to decrease further more, and that means your pressure increases further higher. Okay, this is the working of the rotary compressor. So eventually you are providing a lower pressure at the inlet to a higher pressure at the outlet of the fluid, working fluid. Function of a compressor or a pump is to increase the pressure of the working fluid eventually. I hope this casing and this much is clear. So I just made a diagram of a centrifugal compressor to show. This is your centrifugal compressor diagram. We will deal in detail. It's basically a rotary compressor, part of a centrifugal compressor is a part of a rotary compressor. So now let us see. Let me make the velocity diagram of that blade. Now I will deal with the particular blade of the impeller, okay, and show you velocity triangles of impeller blade. Okay, so we have a impeller blade like this. I will use the same color. You will understand the same things in your fluid machinery subjects also. There also you will see this velocity triangles. Your impeller blades are moving at an angular velocity omega. So here it was moving at an angular velocity. Let me use another color. Omega. Okay. Your impeller is rotating at angular velocity omega. That means, let us say, it is rotating at an angular velocity omega. There is a nozzle which is kept here from where, or the not a nozzle, if I want to say, from a nozzle or from a sump, you are lifting up the fluid. Okay, so the fluid will lift up with the velocity v1 at the section 1. So this is your section 1, and this is your section 2. Okay, section 1 of the blade and section 2. Again, I'm saying this is a top view. Always see, it's a top view which I'm making of the. Now enters at a velocity v1. Okay, now this velocity will have two components. The first one will be vw1, as we have seen, and vf1. Okay, the wall and the flow component. Okay, angle at which it's enter is your nozzle angle or absolute velocity angle at the inlet. So this was your angle alpha. This is your angle alpha. So alpha is nozzle angle or absolute velocity angle at inlet. Okay, this is your angle alpha at which, suppose a nozzle is there from where the fluid enters. Nozzle. So that is why I'm saying it is a nozzle. Okay, it enters through a nozzle at an angle alpha. Now further, your rotor is also moving or you can say blade is also moving with a tangential velocity u1 at this point, u1. Okay, that is v1 into r1 omega from the rotor. So suppose your I, or the center of your impeller, at a distance r1 from here. So that is r1 into omega, and this is at r2. Okay, these are continuously moving. So that will be u2 into u2 will be r2 into omega. Just to show you a visualization. Now let us. You have to always remember two things for making a velocity triangle. That v square, that is your absolute velocity square, should be sum of the squares of the whirl component plus flow component. First is this, that is a Pythagoras theorem. Eventually v1 square is equal to vw1 square plus vf1 square. First condition should always be this. And next, for the relative velocity, if I'm saying my velocity u is still here, suppose this is my velocity u. Okay, velocity u1, this is my velocity. Then from the law of triangle, summation law of triangle, the sum of v, the absolute velocity will be sum of u1 plus v relative 1. V relative, let me draw. Doesn't matter, v relative 1 is this side or this side, the sign will only change, the magnitude will always be remaining same. So don't worry about that. Whatever way you can make the diagram, but always remember these two conditions should always follow. I'll write these two conditions. So this is your v velocity 1. Either it's a turbine or a compressor or a pump, you can make it any of the way, but those two conditions should always be fulfilled. That is, the first condition was v1 square is equal to vw1 square plus vf1 square. Other condition is u1 plus vr1 as per the triangle of addition should be equal to v1. Okay, all right, this is your vr1. I think I should have not made this, written it here. First let me make the triangle, velocity triangle. Okay. Then again it will be coming out, that is the fluid will, what air or working fluid will coming out at a velocity, absolute velocity, let us say v2. V2 is your absolute velocity. Please carefully understand these velocity triangles formulas. Okay, let us say it is coming at relative velocity. Let me again, for a simplicity, let us say it is coming relatively out at a relative velocity 2 here, and the absolute velocity was something like this, v2. Okay, it came out in this direction. Okay, so again this velocity will have two components, of the v2 will have two components, that is your vf2 and vw2. Okay, vw2. From the first law, from the first condition it's satisfied. The other condition is, if I have again I have a u component, u2 component here, I can write it like this. From here till here, I have a u2 component. So I need to have a relative component here, that is vr2. So the condition satisfied, vr2 plus u2 is equal to v2. The other condition also satisfied. And here the diffuser angle, that is your inlet angle, oh sorry, absolute velocity angle at the outlet. This will be your angle beta. This will be your angle. Let me draw beta. So let me write these angles. Alpha is your nozzle angle, or absolute velocity angle at inlet. and beta is your diffuser inlet angle. Why diffuser inlet? Because now when it passes through this, it is going into the diffuser region. Okay. When it exits from the impeller, it goes to the diffuser. So inlet to the diffuser, basically. Beta is diffuser inlet angle or absolute velocity angle at outlet. Absolute, this V2 is your absolute velocity and it is making angle beta at outlet. Absolute velocity angle at outlet. Okay. Again, there are two angles other. Theta and phi are the moving blade angle at inlet and outlet. Moving blade angle at inlet and outlet. How? Let me write here. Theta and phi are moving blade angles at inlet and outlet. Let me show you. So this will be your theta and this is your phi. So at inlet at outlet. How? Okay. All right. Now don't worry about this. What is relative velocity? VR is velocity of fluid along the surface of the vane. Along the surface of the vane. So always remember, however you make the diagram, you have to maintain these condition. That is, V square is nothing but sum of VW square plus VF square. And other condition is absolute velocity can be written as vector law of addition U plus VR. Okay. Rotor plus relative is absolute. Now let us see the triangle ABC. Let me make a triangle ABC for you. So let us use color. Which color should we use? This. Oh, no, it's not. This is A. This is B. And this is C. In triangle ABC. In triangle ABC, from Pythagoras law, you can say AB square is equal to AC square plus BC square. BC square plus AC square. So what is AB? If you see, AB is nothing but VR2 and BC is nothing but complete U2 minus VW2. U2 minus VW2. That will give you length BC. So VR2 is equal to U2 minus VW2 and AC is nothing but VF. Yeah, this much VF. This is your AC plus VF square. VF2 square. Expand it. U2 square, that's VW2 square minus 2U2 VW2 plus VF2 square. And from the condition, VW2 square plus VF2 square is your absolute velocity, V2 square. So you can say this plus this is V2 square. So this is U2 square plus V2 square minus 2U2 VW2 is VR2 square. Okay. Okay. Now, if you take 2 times U2 VW2 that side and this to be here, V2 square plus U2 square minus VR2 square, because this was required, angular momentum change VW to U2 at the outlet and inlet from here. This is required. These two conditions are required for getting the power input. So this will be divided by 2U2. So you will get, sorry, divided by 2, VW2, U2 is nothing but V2 square by 2 plus U2 square by 2 minus VR2 square by 2. Similarly, you can get VW1 U1. Similarly, VW1 U1 will be V1 square by 2 plus U1 square by 2 minus VR1 square by 2. Now put it for, let us say this is your equation number 1. This is your equation number 2. Let us say 2 minus 1 is VW2, sorry, 1 minus 2. 1 minus 2, that is VW2 U2 minus VW1 U1 is nothing but V2 minus V2 square minus V1 square by 2 plus U2 minus U1 plus by 2 plus VR1 square minus VR2 square by 2. Okay. Now we need to understand the term of explanation of each term. What is happening here? Okay. This is your final term. What does each term on the right hand side? So the first term V2 minus V2 square minus V1 square by 2 is basically your impulse effect. Okay. This term, and it means that there is an increase in the kinetic energy of the fluid because you have sucked up the fluid at the section 1 and you are exiting from section 2 at a higher speed. You have increased the kinetic energy of the fluid that needs to be converted into a pressure rise in the diffuser. Okay, then that fluid from section 2 will go into the diffuser. Initially, you increase the kinetic energy by sucking in, by creating a vacuum at a higher speed of the rotation of the impeller. That the fluid discharges through the impeller to the section 2 and it enters the diffuser. It enters the diffuser where the pressure increases by converting that increase in kinetic energy to pressure rise in diffuser. Right. The first term V2 square minus V1 square by 2 is impulse effect. That means it represents increase in kinetic energy of fluid that needs to be converted into pressure rise in diffuser. Okay. The second term, that is your U2 square minus U1 square by 2. What does it represent? That represents that it represents the rise in the pressure corresponding to the working fluid that enter at a smaller radius and leave at a larger radius. So U2 is having a larger radius, R2 is greater than R1 because at section 2 the radius is higher compared to at section 1. If you see, so from impeller eye, R1 is less compared to R2. Okay, so it represents the rise in pressure corresponding to the oops corresponding to the working fluid enters at smaller radius, that is U1, and leaving at larger radius. Okay, so this is nothing but your centrifugal effect. This was your impulse effect. Now the last term, that is the third term, is your VR1 square minus VR2 square by 2, and it depicts reaction or diffuser effect. Now the fluid has entered into the diffuser, so it represents increase in the pressure because diffuser has a diverging section, and because of the diverging section area increase, and to maintain the continuity your velocity has eventually to reduce. That means when the velocity is reduced, the pressure is going to eventually increase. So it represents increase in the pressure as the flow takes place in that diverging passage, due to which your relative velocity decreases from inlet to outlet, and there is a corresponding rise in the static pressure that is happening inside the diffuser. So it represents increase in pressure as flow takes place in diverging passage or diverging section, due to which relative velocity decreases from inlet to outlet, and there is corresponding rise in static pressure. Why static? Because diffuser is always remaining at static condition. Diffuser don't move, only impeller moves in static pressure. All right, let's stop it here, and we will discuss the functioning of centrifugal compressor and the further things in the upcoming tutorial. Hopefully there will be a new next tutorial happening this Friday as well, and the final will be on the next Tuesday. So then we are towards the end of our course. Last two tutorials are left, and you will get a sheet from the NPTEL team where you will have the links for all the recordings of the session as well as the PDF notes, the Google Drive link. If you are new and you have not registered in the course, you are directly seeing, so you can check out the recordings at my YouTube channel. That is, I'll write the name, NPTEL with Varnit. So in the corresponding playlist for the section for the corresponding course, IC engine and gas turbine, you can see week-wise videos, and in each video description you have a link for the Google Drive where you can see the notes of this video. Okay, so if there are no doubts, we can end the session, and I'll see you in the next upcoming tutorial.